Welcome to The Quiet Scientist. I'm so glad you're here. Whether you're curled up beneath a heavy blanket, sitting quietly by a window, or simply letting your thoughts float at the edge of sleep, thank you for spending your evening with me. This is a place for soft science, stories that don't demand anything of you, except the gentle willingness to wonder. Tonight, we're following something strange, invisible, and astonishingly fast. We're going to drift alongside light, not just any light, but light at its limit, because somewhere in the fabric of the universe, light was given a rule. It can go this fast, and no faster. But who made that rule? And why should the fastest thing in the universe have a ceiling? Is the speed of light a suggestion, a law, or a quiet agreement between space and time? I hope this story helps you slow down, perhaps even drift off into sleep. But I'll warn you, this one might be a little too dazzling, too strange, too elegant in its logic. If you stay awake, and you just might, I promise you'll leave with a soft, glowing piece of knowledge tucked behind your eyes. Before we float too far into the cosmos tonight, a gentle like or subscribe would mean the world. It helps. The quiet scientists keep growing, quietly and curiously. And if you're listening right now, I'd love to know where in the world you are and what time it is as you press play. Is it just past midnight, early afternoon, or that in-between moment just before you close your eyes? Now, just take a breath. In, through your nose, let the air move gently into your chest, and out, like the dimming of a distant star. Let's begin with the beginning, not the Big Bang, but something a little more human, something with fire and fear and wonder. Imagine this, tens of thousands of years ago. You sit near a fire. You are not a scientist. You are not named, but you watch. You see the light of the flames flicker across the face of someone you love. You see their eyes reflected, and beyond them, just darkness. At some point, maybe you notice that lightning flashes before thunder claps. You didn't have words for velocity or frequency or electromagnetic radiation, but you noticed the delay. That flicker in the sky reached you before the world had time to rumble. And so, a seed is planted, a quiet realization. Light moves, and it moves fast. Thousands of years pass. Civilizations rise and fall. Candles are lit, torches waved, stars mapped by shepherds and scholars. But the question remains unanswered. How fast is light? In ancient Greece, thinkers like Empedocles and Aristotle had differing opinions. Some believed light traveled, that it moved from its source to your eyes. Others thought it was instantaneous, that it simply existed everywhere at once, like a divine presence. No need for motion, they thought, just illumination. But how do you catch something that might move too fast to be caught? You try. In the early 1600s, Galileo Galilei stands with a lantern on a hilltop. His assistant stands on another hill, far away. The idea is simple. Flash your lantern. When your partner sees it, they flash theirs back. With enough distance and a fast enough stopwatch, maybe you can catch light in the act of traveling. But it doesn't work. Not really. The delay is too small. Human reaction time gets in the way. The light comes and goes before your brain even registers it. Still, the attempt is beautiful, a kind of lantern-lit poetry, trying to catch the wings of something invisible, trying to measure the heartbeat of the cosmos with nothing but a flame and hope. As time moves forward, people stop trying to measure light directly with their eyes. Instead, they look at the sky, and that's where the first real clue appears, not from Earth, but from a distant moon. In the 1670s, a Danish astronomer named Ole Rømer is watching Jupiter. Or, more precisely, he's watching one of Jupiter's moons, Io. It orbits regularly, like a cosmic clock, but sometimes Io appears a little late, and other times it shows up a bit early, Roemer realizes something extraordinary. When Earth is moving away from Jupiter, Io's eclipses seem delayed, and when Earth moves closer, they seem to arrive too soon. The only explanation? Light takes time to cross space. The distance matters. The delay matters. He calculates, roughly, that light moves at a finite speed, not infinite, not immediate, not godlike, but fast, very fast. And with that discovery, something subtle but profound shifts in the human mind. Light is not just something we see. It is something that moves. And like all things that move, it must obey rules. But what kind of rule could apply to something so unlike us? It has no mass, no limbs, no thoughts. It travels in waves and in particles. Depending on how you look, it's a trickster, a messenger. And now, a mystery with a number attached. Still, the number isn't right yet. Roemer's guess is rough. It will take centuries, more moons, more mirrors, and eventually, more math, to pin it down precisely. But the truth is already out. The cosmos has a speed limit, not because we said so, but because it does. Even now, lying there, eyes soft, mind open, you are surrounded by light. The glow of your screen, the moonlight on your floor, the starlight from 1,000 dead suns. And all of it is traveling. All of it has obeyed the limit. As we drift toward the next part of our story, we leave behind the hilltops and oil lamps, the stargazers and their notched tools. We move instead toward an idea that light, as strange as it is, isn't free to go wherever or however it pleases. Something, somewhere, has told it this much, and no more. You feel the echo of that lantern still glowing in your mind as the story carries you forward. There's something tender about those early attempts to understand light, like watching a child try to catch a firefly in cupped hands. You know it's there. You've seen the flicker, but it's always faster than your reach. Tonight, we're still moving slowly through that ancient curiosity, not with haste, but with the same patience the stars seem to have, the patience to shine across centuries, the patience to wait for us to notice, before telescopes, before experiments, before even the names of things. There was only the experience of light, and the mystery of how fast it arrived. Close your eyes for a moment. Imagine yourself in a cave, your only light source a flickering flame dancing atop a lump of hardened animal fat. That pale yellow glow fills the space just enough to keep you from bumping into stone, but beyond its reach, only blackness, a thick kind of silence you can almost hear. Suddenly, a storm. A bolt of lightning tears across the sky outside. You see the flash before your body reacts. Before you hear the roar, your senses stretch like a net, one that only barely catches the edges of something ancient and wild. Even then, in your most instinctive state, you feel that delay. The light arrives first, sound trails behind like a sheepish sibling, and in that split-second gap, a question is born. Why did one get here before the other? You don't call it the speed of light. You don't measure it in meters per second, but something in your body knows. Light is quick. Light does not wait. And so, over generations, humans begin to wonder, is light like sound? Can it be slowed or stopped? Is it something that travels like birds or arrows or wind? Or does it simply exist? For a long time, people weren't even sure that light moved at all. Some ancient thinkers believed that sight happened because rays shot out from your eyes, like invisible feelers, and touched the world. The object didn't send light to you. You reached out and claimed it with your gaze. The world only existed when you looked at it. It's a strangely beautiful idea, and in some ways, you can understand the impulse behind it. When you stare into a flame or up at the stars, it does sometimes feel like your attention has weight. like it could cross the space between you and the thing you're watching. But then again, why couldn't you see in the dark? And what about the way shadows move? Why did some objects glow and others disappear when night came? If your eyes created vision, shouldn't you see equally well in any direction, regardless of the light? Slowly, and with quiet persistence, the idea shifted. Light, it seemed, came to you from the sun, from the moon, from stars and lamps and fire. And if it came to you, it must be moving. And if it's moving, it must be doing so at some speed. But how fast? That question hovered, like a spark above a candle, flickering and fragile. Let's return to the 17th century, not to the mountaintop experiments of Galileo this time, but to the mind of a man named René Descartes. Descartes imagined the universe as a series of mechanical interactions, like a great cosmic clock. Its parts clicked and turned according to predictable rules. He believed that light must move like pressure in a stick. You push one end, and the other end moves instantly, without delay. In his mind, light didn't take time. It simply happened. But not everyone agreed. Others thought maybe light did take time. Maybe it wasn't instantaneous, but just impossibly fast. They searched for ways to measure it: mirrors, lenses, spinning wheels, anything that might slow it down enough to be seen, to be counted, to be caught. The breakthroughs came slowly, flickers of understanding that built upon one another like layers of translucent silk. Each new idea didn't replace the old ones so much as gently correct their shape. You begin to feel it now, don't you? That strange blend of simplicity and mystery. Light surrounds us, touches us, defines the way we see, and yet we still struggle to describe it, not because it hides, but because it's always just ahead of our grasp. Consider this. Light allows you to see the world, but you never really see light itself. You see what it touches, what it bounces off of, what it reveals. But the beam itself, it passes through space like a whispered thought, not seen, but known. And if you've ever stared through a window at dusk, you've felt the dreaminess of it, the way light can soften edges, wrap shadows around corners, make the familiar look foreign. It isn't just fast, it's transformative. This is the world we inherited. A world defined by speed we couldn't measure, only sense. A world that flickered before it explained itself. But it wouldn't stay that way forever. Slowly, ever so slowly, we develop better eyes, not in our skulls, but in our instruments, telescopes, lenses, machines that could measure moments smaller than a blink. And as we moved into this next phase of human curiosity, we no longer had to guess. The cosmos had left clues, and we had finally built tools steady enough to read them. In the next part of our journey, we'll peer through one of those clues, not in a lab, but in the night sky. Because while Galileo looked for light on mountaintops, another man looked to Jupiter and found something astonishing. Not just moons, but delays. Not just shadows, but signals. A quiet code written in time itself. So, rest your eyes for a moment. Feel the memory of that lightning still shimmering on your eyelids. That ancient knowledge, older than language, whispering again, light does not wait. You're still holding on to that echo, the shimmer of lightning behind your eyes, the sense of something moving just ahead of understanding. And now, we follow the thread deeper, from firelight to starlight, from guesses to the beginning of the chase. It begins quietly, as many great discoveries do. No fanfare, no glowing eureka, just the slow, deliberate gaze of a man peering through the lens of a telescope toward a faraway gas giant. His name is Ole Römer, and he doesn't set out to change the world. He's simply trying to tell time by the heavens. It's the 1670s in Copenhagen, and Jupiter, like a patient teacher, has moons that orbit with a rhythm so reliable. You can set your watch by them. One moon in particular, Io, vanishes and reappears at exact intervals as it moves behind the giant planet. Or at least, it should. But rumor notices something strange. Io seems to lag behind schedule when Earth is farther from Jupiter. And when Earth draws closer again, Io arrives too early. These aren't random errors. They're patterned, predictable. They speak in timing, not in noise. He doesn't have the words for it yet, but what Romer has stumbled upon is delay, not from the moon, but from the light. The farther the light has to travel, the longer it takes to arrive. It's as though the universe exhaled slowly, and for the first time, someone listened for the pause. Let's imagine it now. You're watching Io disappear behind Jupiter's thick shadow. You know when it's supposed to emerge. You've seen it so many times that the rhythm lives in your bones. But this time, it's late. Only by a few minutes, but late. What could cause that? Romer suspects that light doesn't reach us instantly, that it moves and it takes time to do so. He calculates, roughly, the speed based on how late Io appears when Earth is farther away, and how early it appears when Earth is near. His result isn't exact, but it's bold. He dares to say the unsayable. Light has a speed, a finite speed. And in doing so, he unlocks a new layer of reality. Light is not just a property of vision. It is not an aura or a gift of the gods. It is a thing that travels, a runner across the cosmic track, not a god, but a messenger. The implications are quiet but profound. If light takes time, then what you see is never the present. It is always a memory, a moment that is already past, even now. Look around you, the light bouncing off the page, the screen, the wall beside you. It's already gone. The moment has already ended. You're just receiving the message. This applies not just to moons and stars, but to everything. The sun you see out your window, it is the sun from 8 minutes ago. The nearest star beyond it, that light has traveled over 4 years just to reach you. You live, always, in a gentle delay. It's strange to think of time as stretchy, but light teaches us that truth. The farther it must go, the older it becomes, and so do the things it reveals. Even with Romer's discovery, the world doesn't quite erupt. His calculations are appreciated, debated, refined, but it will take time for the idea to fully settle into the collective mind of science. Still, a spark has caught. The chase is on. Scientists now begin trying to measure light with more precision. Some bounce it off mirrors. Others spin toothed wheels in dark corridors, trying to catch the flicker as light returns. It's like timing a ghost. And yet, slowly, they get closer. Each new method gets more precise, and each new result draws closer to a number, a limit, that seems to repeat itself, no matter the tool. A kind of whisper from the universe, gently insisting, this is how fast light can go. It's not infinite, but it's fast. About 299,792 kilometers per second, roughly 186,000 miles per second. It's so fast. You need 7 complete orbits of Earth in a single second to keep pace. And yet, it is not instant. That's the part that matters most. Because if something has a speed, it also has a boundary. And boundaries are where physics becomes philosophy. Why should anything be capped at that speed? Why that number, and not another? Is it a cosmic coincidence? Or does it protect something deeper? Something about the shape of time itself? These are the questions we now begin to ask. But the beauty of Romer's discovery is that he asked without asking. He didn't know what he'd found. He just followed the rhythm of the moon. And in doing so, he pulled the curtain back on the speed of all things seen. Tonight. Maybe you find yourself wondering, how strange is it that our eyes depend on delay? That all sight is hindsight? That light must run, and that we must always wait? and still, we hardly notice. The delay is so slight, so gentle, that daily life doesn't flinch. But when we peer into the cosmos, into galaxies billions of light years away, the delay becomes enormous. We are looking not just across space, but into the deep vault of time. And somehow, it all starts with a tiny moon dancing around Jupiter. So, as you rest now, remember this: the light in your room, however faint, is moving, traveling, arriving, and you, quietly and without effort, are catching it. In the next part of our journey, we'll follow the thread forward again, away from the moons and into the strange invisible medium that once held science in its grasp, the mysterious ether, a substance once thought necessary for light to exist, a presence all around and yet never proven. It's a story of searching for what isn't there and realizing, softly, that light may not need anything but space itself. So, we continue, from moons that whisper in delay to the fabric of space that seemed, for a long time, to whisper back. By now, light has become more than just a glow, more than a flicker at the edge of a cave. It's a wave, a traveling thing, and like any wave, it must have something to ripple through, or so scientists once believed. After all, you've seen waves before, on water, in sound, even in the rustling of leaves. Waves need a medium, a surface, a substance to move across. You cannot ripple without something to ripple through, or so it seems. And so, as light was being studied more seriously in the 18th and 19th centuries, a question settled gently into the minds of scientists. If light is a wave, then what is it waving through? Their answer was both elegant and invisible. They called it the ether, or more formally, the luminiferous ether, a delicate, all-pervading medium that filled every corner of space. It had no smell, no weight, no color, but it had to be there, they thought, because how else could light travel? To them, ether was like the stage beneath the dance, unseen, but essential. Without it, there could be no light, no movement, no connection between the stars and our eyes. It filled the void, even if no one had ever touched it. You can almost picture it, a universe gently saturated with this ghostly material. Every beam of starlight, every flicker of flame, every glint on the surface of a pond, all of it gently rippling through an invisible ocean that no one could see. And so, they tried to find it. They weren't looking for proof that light moved. That much had been accepted. What they wanted now was evidence of what light moved through. They believed Earth must be drifting through the ether like a ship through still water. And if you could measure that drift, even the smallest difference, it would reveal the ether's presence. Enter two patient men, Albert Michelson and Edward Morley. It's the late 19th century, and science has grown quieter, more precise, less speculative poetry, more methodical whispering with nature. Michelson and Morley design an experiment with mirrors, lenses, and astonishing care. Their setup is meant to detect the Earth's motion through the ether by comparing the speed of light in different directions. The idea is simple in theory. If Earth is moving through the ether, then light traveling in the direction of that motion should behave differently than light traveling across it. Think of it like a swimmer in a river. You'd expect it to take longer to swim upstream than across the current. So, they build the interferometer, a delicate machine that splits a beam of light, sends the two halves along perpendicular paths, and then recombines them to look for interference, tiny shifts in the waves that would betray the ether's flow. They wait, they measure, they refine, they hope, and they find nothing. No shift, no interference, no proof of ether. The light travels at the same speed in all directions, as if the Earth is not moving through anything at all. The result is unexpected, disorienting, and yet, somehow, deeply quiet The ether, it seems, does not exist, but the implications don't shout. They settle in slowly, like morning fog lifting off a lake. If light needs no medium, if it can move through the vacuum of space without rippling anything, then it is stranger than we thought. It is not like sound or water or wind. It is its own thing, self-sufficient, unbothered. This was hard to accept. The idea of ether had been beloved, a comforting background, an invisible structure that held things together. Letting go of it meant facing a more haunting truth. The vacuum was truly empty, and light, the most familiar of things, traveled through nothing, without need, without help. What kind of wave could do that? Even now, you might feel a bit of resistance in your mind. You're used to the idea that light moves, but moves through what? The idea of something moving through nothing feels slippery, unnatural, like a boat floating with no water, or a voice sounding without air. And yet, that's what the Michelson-Morley experiment taught us. Light doesn't need a carrier. It simply is. And it always goes at the same speed, no matter who's watching. This may seem simple, even boring, but to the scientists of the time, it was baffling. Because if you can't detect motion through space, then what is space? And what does that say about time? You see, the ether wasn't just a theory about light. It was a way to hold on to certainty, to anchor the universe to something fixed. Without it, everything began to drift, especially the concept of simultaneity. If there is no preferred frame of reference, then your now might not be the same as mine. Time itself becomes negotiable. And that's where we leave our scientists, staring at their results, unsure whether they've failed or discovered something profound. Because sometimes, absence is the loudest finding of all. Tonight, as you rest, you might imagine space around you as truly empty. Not frighteningly empty, but peacefully so. No invisible jelly, no hidden web, just pure, open distance and light, slicing through it like silk. In the next part of our journey, we'll meet a young man who read the results of that experiment and smiled, not because he knew the answers, but because he knew the questions were finally good enough. A man who imagined riding on a beam of light, and in doing so, changed the very shape of space and time. His name, of course, is Einstein, and his thoughts would become the next great lantern in this slow illumination of the universe. But, for now, let yourself drift in this quiet mystery. Light moves through nothing, and yet, it always finds you. You're still floating in that quiet void, the emptiness where the ether was meant to be. The silence after Michelson and Morley's failed detection feels like the hush after a candle is blown out. But not a loss, not an absence, more like a breath being held, just before a new thought arrives. And that thought belongs to a curious young man who worked at a patent office. He wasn't famous yet. He wasn't surrounded by blackboards or laboratory assistants. Just a desk, a pile of technical documents, and a restless mind. His name was Albert Einstein, and he spent his quiet afternoons not just reviewing patents, but thinking about trains, about clocks, about lightning and movement and time, and, most of all, about light. You might expect that a scientific revolution would begin in a lab or observatory, but this one began in imagination, the kind you might fall into just before sleep, the kind that lets you feel things that haven't happened yet. Einstein asked a simple, dreamlike question. What would it feel like to ride on a beam of light? Close your eyes for a moment and try to picture it. You climb aboard a wave of light as if it were a train, rushing forward at 186,000 miles per second. You're not catching up to the beam. You are the beam. You're moving alongside it, in perfect step. What do you see? The answer, according to Einstein, is strange and beautiful. If you could ride with light, the world around you would seem frozen. Everything would halt. Time itself would stop. But how could that be? Einstein realized something no one had fully grasped before, that the speed of light isn't just fast. It isn't just consistent. It's constant. For everyone, everywhere, no matter how they're moving. It's not like a car or a sound that behaves differently depending on how fast you're going toward or away from it. Light doesn't care. Its speed is always the same. But if that's true, then something else has to give. Because if you're running toward a light beam and its speed doesn't increase, and if you're moving away from it and its speed doesn't decrease, then your own experience of time and space must be changing to make up the difference. That's where things get soft and stretchy. Time, Einstein proposed, is not a rigid thread. It's more like a ribbon, able to bend, twist, and stretch depending on how fast you're moving. When you speed up, your clock ticks more slowly compared to someone standing still. Not because the clock is broken, but because time itself has softened around you. And space, it stretches too. The faster you move, the more compressed your direction of travel becomes, like squishing the front end of a moving train. It sounds impossible, dreamlike, but the math worked. And more importantly, the math explained things no one else could. Einstein called it his special theory of relativity, and with it, he gently rewrote the universe. But the most profound part, the truly strange, sleepy part, is this. All of it flows from the speed of light. That one number, that one limit. You might think of it as a kind of anchor, in a universe where everything else is relative, where motion, time, and space can all shift depending on your perspective. The speed of light stays perfectly fixed, like a quiet star that all other truths must orbit around. Imagine now, two people standing far apart on a long, empty train platform. A lightning bolt strikes the tracks exactly between them. The flash races toward both people at the same speed. But if one of them is moving, say, riding a train, they might perceive the flash as reaching them sooner or later than the other person. So, who's right? Einstein's answer was radical. They both are. There is no single, universal now. What you perceive as simultaneous may be completely different for someone else moving differently through space. Time becomes personal. Not subjective like opinion, but dependent on motion. It's almost romantic, isn't it? That time is not universal, that each of us carries our own little river of moments, flowing at slightly different speeds depending on how we move through the world, and all because light refuses to change its pace. Tonight, as you lie still, you are part of this strange ballet. Even now, Earth is moving, spinning on its axis, orbiting the sun, drifting through a galaxy that itself is gliding through the vastness of space. You are not still, not really, but light doesn't care. No matter how fast you move, no matter your direction, it always rushes toward you at exactly the same speed. It is the one rhythm that never falters. And if that sounds abstract or hard to grasp, think of it this way. If two people are traveling at different speeds and both measure the speed of light, they will get the same result. Always. Which means their time and their space must be adjusting, imperceptibly, to compensate. You might never notice it in daily life, but GPS satellites must. Their clocks tick differently than ours on Earth because of their speed and altitude. Engineers must correct for time dilation, the stretching of time, or else your directions would slowly drift, mile by mile, off course. Einstein's insight wasn't just dreamy. It was real, practical, soft in its imagination, sharp in its consequences. And yet, it began with a childlike question. What if I could ride a beam of light? In the next part of our journey, we'll look at what that speed, that limit, actually means for the universe itself. Not just for clocks and trains and satellites, but for reality. Why does this number exist at all? Why can't we go faster? But for now, Let this image settle in your mind. Time, stretching softly, space, bending quietly, light, gliding through the dark, not faster than possible, but exactly as fast as the universe allows. You're still drifting alongside that quiet beam of light, still feeling the ripple of Einstein's imagination. You can almost sense the world around you growing softer, more flexible, time loosening its grip, space adjusting its threads like fabric pulled gently in opposite directions. All because the speed of light stays still, constant, calm. Now we ask a quieter question. Not just how fast is light, but why is that its limit? Why that number? Why 186,000 miles per second? Why not 200,000? Why not infinity? There's something oddly comforting about limits, even strange ones. They give the universe structure, a quiet order beneath the chaos. And the speed of light, it turns out, isn't just a limit on light. It's a limit on everything, on causality, on movement, on the very way the universe tells its own story. You might think of it like this. If the universe is a great novel, then the speed of light is its grammar. It defines what can follow what. Which events can touch each other? Which moments can be linked in sequence? Without it, the sentences of time could tangle, stories could unravel. Let's try a simple picture. Imagine you're tossing a pebble into a still lake. Ripples radiate outward, gentle and predictable. The lake, in this analogy, is space-time, the combined fabric of existence. The ripples, they're changes, messages, events trying to affect other events. But there's a rule. Those ripples can't move faster than light. That's the built-in speed limit of the fabric itself. Nothing, no signal, no particle, no nudge can move faster than that ripple. If something did, it would mean that effects could arrive before causes, that you could hear the echo before the shout, that someone could trip before the floor rose to meet their foot. Without the speed of light, time itself could lose its direction. And that's not just unsettling, it's dangerous for logic, for physics, for meaning. Because the speed of light doesn't just cap how fast we can travel, it caps how quickly information can move. And without that cap, cause and effect, the quiet heartbeat of reality could get scrambled. So, it's not just about light, it's about structure. The universe has drawn a boundary, not out of cruelty or constraint, but to keep itself coherent. You might imagine space-time as a great, smooth fabric stretching in every direction. Whenever something happens, a spark, a thought, a burst of energy, it sends out ripples. But those ripples cannot outpace light. They can't cheat. They can't rush ahead. And that's a gift, because it means there's order, sequence, a softness to the unfolding of events. Even black holes, those mysterious places where gravity becomes overwhelming, still respect this rule. Nothing, not even light, can escape from inside. And that's why we call their boundary the event horizon. Once light passes that line, it's cut off. Its story ends for us. The universe cannot see beyond that edge, not because it won't look, but because the rules won't let it. It's strange, isn't it? That something so abstract, a number, a velocity, can hold such weight, that it can shape the motion of galaxies and the unfolding of thoughts. But that's the nature of constants. They are the quiet bones of the cosmos, rare, fixed, and utterly unshakable. And yet, this rule is not brutal. It doesn't demand obedience with force. It simply is. Like gravity, like time, like a whisper that's always been part of the silence. And it's not as if things want to go faster and are held back. For most particles, the speed of light is not a goal. It's an unattainable dream. You see, to reach that speed, an object with mass would need infinite energy, and infinity, as you may have noticed, is rather difficult to come by. So, the rule is self-enforcing, not because anything is pushing back, but because reality is built that way. Now, if you're lying there wondering why that number, specifically, why 299 seems 792, 458 meters per second, there is an answer. But it may not feel very satisfying. That number arises from the units we use to measure distance and time, and how we've defined them based on physical constants. The deeper truth is that the speed of light is not so much a product of the universe as it is a definition of how space and time relate to one another. It's like the slope of the universe's own graph, a fixed ratio between the way we measure distance and the way we measure duration. And what's perhaps even more magical is this. Once we accepted the constancy of light's speed, we began to see that the universe wasn't built around time and space separately, but around a fusion of the two, space-time, a kind of fabric, four-dimensional and softly woven, that flexes and curves and ripples under the presence of mass and energy. And the threads that run through this fabric, they're laid out according to the speed of light. That number, fixed and luminous, defines how steep the threads are, how steep a life can be lived, how cause can lead to effect without jumping the track. You may never feel this in daily life. Light moves too fast, time ticks too evenly, the world seems stable, but at the edges, in particle accelerators, in the whisper of starlight that's billions of years old, in the glow of your phone as it maps your location by satellite, the limit is real. It shapes the flow of everything you see and everything you are tonight. Perhaps you let go of the idea that faster is always better. That limitless speed would be a gift. In truth, without this boundary, the universe would unravel in quiet chaos. It would lose its melody. The narrative would break. Instead, we are given a tempo, a pace, a rhythm to walk beside. Not to surpass, but to understand. In the next part of our journey, we'll ask the natural follow-up. What happens when something tries to go faster than light? What breaks? What bends? And why does nature seem so determined to hold the line? But for now, picture light not as a bolt or a flash, but as a thread, quiet, steady, unrushed. The thread that sews space and time together, stitch by stitch, across the fabric of everything. That thread of light still glows faintly in your thoughts, not racing, but moving with absolute certainty, stitching time and space together with every silent second. In the quiet between heartbeats, you begin to sense its importance, not just as a limit, but as a kind of boundary that holds the universe gently in place. Now, we arrive at the natural curiosity. What if something could break that boundary? What if there were a way to go faster than light? What would happen to time, to space, to meaning itself? It sounds like science fiction, a spaceship accelerating beyond the stars, punching through some unseen barrier and disappearing into hyperspace. But to physicists, this idea is less a story and more a warning, because faster-than-light motion isn't just difficult, it threatens the very structure that holds reality together. Let's ease into it. Imagine two people, you and someone else, standing far apart. You send a message, a beam of light, a signal. It travels toward them, obeying the cosmic speed limit. They receive it and respond, cause and effect. First you speak, then they answer. Now, imagine you send that message faster than light. Suddenly, strange things begin to happen. In some frames of reference, that is, from someone else's point of view, your message doesn't just arrive faster, it arrives before you send it. Time flips. Cause and effect are reversed. The reply arrives before the question. And in that tiny crack, logic begins to dissolve. If such a thing were possible, you could create paradoxes, effects that precede their causes. You could warn your past self of something that hasn't yet happened. You could send a signal that prevents itself from being sent. And when reality becomes tangled like that, Physics can no longer hold it together. This is why the speed of light is more than just a number. It's a boundary drawn in time, a soft line that separates before from after. Go faster, and time may no longer flow forward. It might not flow at all. This isn't just an abstract idea. It's built into the equations that describe how motion and time interact. The closer something moves to the speed of light, the more energy it needs to keep accelerating. But here's the twist. As you approach the speed of light, that energy requirement doesn't just rise, it climbs toward infinity. You could pump in more fuel, more momentum, more push, but you would never quite get there. The finish line would stretch farther with every step. Like chasing the end of a rainbow, it always slips just out of reach. And if you try to cheat, if you somehow could jump past light's speed, the math breaks. The equations produce imaginary numbers. Time becomes undefined. Mass becomes unstable. And the story of your journey no longer makes sense. This is why nothing with mass can ever reach, let alone exceed, the speed of light. The universe has built this rule into its bones. But light itself can go that fast. Why? Because photons, the tiny particles of light, have no rest mass. They don't carry weight in the usual sense. They aren't being pushed forward like a train or a rocket. They're born into motion, already traveling at light speed from the moment of their creation. They don't accelerate. They don't slow down. And strangely, from the point of view of a photon, if you could somehow imagine such a thing, no time ever passes. It is emitted, it is absorbed, and in between, there is no between. The journey is instantaneous from its own perspective. This is part of why faster-than-light travel isn't just unlikely. It would require violating the very nature of time and space. It would mean that asking particles to become imaginary, asking moments to exist out of sequence, asking effects to untie their own causes. And so, the universe resists, not angrily, not violently, but firmly. There are ideas, soft, speculative dreams of loopholes, concepts like wormholes or warp drives, theoretical models where space itself bends or folds, allowing shortcuts without breaking the speed limit, like tunneling through a mountain instead of climbing over it. But even those ideas, elegant and mysterious as they are, don't truly go faster than light. They go around the rule, not through it. The limit still holds. You might wonder why the universe is set up this way. Why impose such a limit in the first place? Perhaps it's not about keeping us slow. Perhaps it's about keeping time meaningful, about giving events an order, a before, a during, an after. Without that, everything could happen all at once, or not at all. And for a mind like yours, a mind that remembers, that imagines, that dreams forward, the flow of time is precious. It's not just the medium of change, it's the rhythm of awareness. So, tonight, as you rest, let go of the race. There is nothing to outrun, nothing to chase. The universe has already given you the perfect pace, slow enough to savor, fast enough to witness. The light that enters your room, touches your face, scatters through your dreams. It follows the same rule as the light from distant galaxies. Always the same speed, always the same calm urgency. And perhaps that's what makes it beautiful. Not its speed, but its steadiness. In the next part of our journey, we'll explore how this limit creates a kind of shape in time, a structure that cradles every possible moment within it, something called the light cone. A name as soft and strange as the thing it describes. But for now, stay with this thought. Nothing goes faster than light. And yet, the universe has never needed anything to. So you lie still now, breathing in the quiet comfort of certainty. Light, for all its wild speed and elusive nature, is bound by a rule, not harsh, but elegant. Not a barrier to defy, but a path to follow. And out of that one rule comes something even more beautiful: structure. Because when light has a limit, time begins to take shape, not just as hours and minutes, or as the ticking of clocks on distant satellites, but as a landscape, something you could almost walk across if your steps were quiet enough. And at the heart of that landscape is something both simple and profound, something physicists call the light cone. Don't worry, it's not a sharp thing, not a danger. It's more like a diagram you might find etched in the corner of a dream. Imagine this. You are a single point in space and time, not a body, not a name, just a moment, a dot. Now, imagine a flashlight at that exact point, flicked on in the stillness. The light radiates outward in all directions, forming a glowing sphere that grows larger with every tick of the clock. That expanding bubble represents everything your moment can possibly reach. Every place your signal, your voice, your effect can travel. Bound, of course, by the speed of light. Now, picture this bubble not in 3 dimensions, but folded into a graph of space and time. Suddenly, it isn't a sphere anymore. It becomes a cone, one that stretches outward and forward, like a gentle trumpet of possibilities. This is your future light cone. Everything inside it is what you could one day touch, influence, or affect, if you gave it enough time. But that's only half the story. Flip the direction. Imagine the cone pointing downward now, narrowing into the past. This is your past light cone, the region of space-time from which information could have reached you, events that could have shaped you, the stars that could have shined on your ancestors, the signals that had time to arrive. Anything outside those cones, beyond the spread of light in either direction, is causally disconnected from you. It exists, yes, but it cannot touch you. Not yet, not ever, unless the rules change. And this is what the light cone teaches us, that reality isn't just happening all around, all at once. It unfolds within limits, gentle, mathematical boundaries that cradle cause and effect like a lullaby. It means that your now isn't the same as someone else's. Not if they're far enough away, not if they're moving differently through space. Their past light cone overlaps yours only partially. Their future diverges at an angle. It's like watching 2 pebbles dropped into a pond at different spots. The ripples may meet, or they may not. But each set of ripples defines its own world of influence. You might think of your life, in this context, as a continuous climb up the spine of the cone. At every moment, the base of the cone widens, your future growing larger, your reach extending farther, yet always bound by that universal slope. That slope, the edge of the cone, is defined by the speed of light. It's the steepest any signal can travel, the fastest any event can catch up with you. And because nothing can go faster, nothing can reach you from outside that boundary. No echo can arrive before the sound. No beam can blink in from nowhere. The light cone becomes a kind of compass, a soft geometry of what is real, what is possible, and what is forever out of reach. And yet, within those cones lies everything that matters. Every person you've ever spoken to, every book you've read, every sunrise you've watched or memory you've shaped, all of it happened within your past light cone. It's not limiting, it's defining. Because in a universe without boundaries, nothing would be knowable. There'd be no way to say, this happened because of that. Everything would blur together like colors on wet paper. But with the light cone, we are given shape, sequence, story. Even time travelers, in science fiction, feel the tug of the cone. In most stories, they can't go just anywhere. They must bend around the edges, slipping carefully through the cracks of what the light cone allows. And in real physics, the cone remains unbroken. Even the most speculative theories, wormholes, quantum entanglement, exotic particles, all must in some way, reconcile themselves with this shape, with this quiet rule that says, here is what can influence you. Here is what you can touch in return. It may sound lonely, but it isn't. Because when you look up at the night sky and see the light from a star hundreds of years old, you are living proof of the cone's embrace. That light reached you. It found its way into your slice of space-time. The moment it left its star, it entered the future light cone of a point that would become you. And now, it glows softly in your eyes. Tonight, as you rest, you are wrapped in your own light cone. It hums around you, filled with possibilities. Maybe the light from a distant galaxy is just arriving, meeting you at exactly this second. Maybe a thought you'll have tomorrow will ripple forward, touching someone else's future cone, and somewhere out there, in a far-off part of the universe, someone else's cone may already be brushing against yours, not through motion, but through light. In the next part of our journey, we'll turn inward again, to the curious passengers of that light, the photons themselves, tiny, weightless, timeless messengers. What makes them so special, and how can they move so fast when everything else is held back? But for now, hold on to this image, a cone of light, gently unfolding through space and time, with you always at its center, not trapped, but held, not static, but constantly expanding. You are not separate from the universe's rhythm. You are the rhythm. That cone of light still expands softly around you, a gentle geometry of what can be touched, what can be known, and along the edges of that cone, at its very boundary, are the travelers. The ones that move right on the speed limit, never faster, never slower. The ones who know no time, no rest, no mass. They are called photons, and they are unlike anything else you know. Most things in the universe carry weight. Rocks, planets, atoms, air, even you. Weight is everywhere, and weight means inertia, resistance to change. If you want to move something, you must push. If you want to move it faster, you must push harder. But photons don't play by those rules. They have no rest mass, no inertia, no baggage. It's as if they travel through the universe with nothing packed, no body to slow them down, no suitcase full of protons or neutrons, just themselves, pure energy, shimmering through the void. This is what allows them to glide effortlessly at the speed of light. Not because they try harder, but because they have nothing holding them back. And here's something even stranger. Photons don't accelerate. They don't start at zero and build up speed. The moment a photon is born, perhaps from an atom-changing state, or from a star burning hydrogen, it immediately moves at light speed. No warm-up, no waiting. Now, pause for a moment and imagine that. Imagine being born into motion, not launched, not thrown, but existing only as motion. That's what a photon is. It doesn't have a before and after the way we do. Its entire life is a single unbroken movement through space. And in its own strange way of existing, time does not pass. That's not just poetic. It's what the math tells us. From a photon's perspective, if such a perspective could be imagined, the journey from star to eye is instantaneous. There's no middle, no ticking seconds. It leaves, it arrives, all at once. Of course, you experience time. You might look at starlight and think, that took 8 years to get here, or that photon's been traveling for millennia. And you're right, from your frame of reference. But for the photon, there is no sense of travel, no delay, no time. This timelessness is part of what makes photons so unique. They exist on the very edge of our experience, at the boundary between time and no time, between cause and effect, between here and there. They are messages written in pure energy, carried across impossible distances, arriving always at just the right moment. And yet, Despite their speed and subtlety, photons are not invincible. They can be absorbed, scattered, bent. Even though they're massless, they still interact with gravity. They still follow the curves and warps of space-time, like dancers guided by an unseen hand. Think of a beam of light passing near the sun. You might expect it to move in a straight line, unbothered by planets or stars, but it bends. Gently, gracefully, it curves along the gravity well, not because it chooses to, but because space itself is curved and light must follow. Even without mass, photons still obey the rules, or maybe they are the rules. Because wherever light goes, it reveals. It marks the path of possibility. It lets the universe see itself. It brings color to shadow, shape to emptiness, warmth to cold, and all the while, it carries no weight. You may never meet a photon face to face. It's not something you can hold or store, but you see them constantly. Every time you open your eyes, every color, every shadow, every glint, those are photons arriving, completing their journey, disappearing the moment they land, and yet they leave a trace, an impression, a memory of motion. Even now, the light in your room is full of them. Photons from lamps, screens, stars. They bounce and reflect and scatter, some entering your eyes, some landing softly on your pillow. And each one moves at the same unchangeable pace. This sameness is important. It's what allows our world to feel stable, predictable. Photons don't vary in speed. Red light, blue light, radio waves, gamma rays. All are just different expressions of the same thing, electromagnetic radiation. And in a vacuum, they all move at the same speed. The difference lies not in how fast they go, but in how they wave, some wide and slow, some tight and fast. But the pace remains constant, always. And because of that, we can build telescopes, fiber optic cables, laser surgery, solar panels, all of it made possible by the reliability of the photon. But perhaps the most humbling thing about photons is how much of the universe depends on them. Not just for vision, not just for heat, but for connection. Think of a tree reaching for sunlight. Think of a solar cell catching power from the sky. Think of your own skin warming under the gentle touch of morning. All of it is light. All of it is photons. And every single one traveled here, bearing no mass, no delay, just motion. There's a kind of lesson in that even without weight, you can carry meaning, that even the smallest, lightest thing can go the farthest. That being fast doesn't mean rushing. It means never stopping. So as you lie here now, eyes soft, body still, let the photons keep arriving. Let them glide across the room, through the windows, into your dreams. They've traveled so far to find you. Not hurried, not late, just precisely on time. In the next part of our journey, we'll explore that strange idea further, that for photons, time doesn't pass. We'll ask what it means to live outside of time, what it means for something to exist between moments, and how light reminds us that not everything needs a clock. But for now, remember this: photons carry no luggage, and yet, they carry the whole visible universe. You're still lying quietly beneath the soft arrival of photons, those weightless messengers slipping gently across your skin and into your eyes. They've traveled immense distances without rest, without aging, without changing speed. And now, we turn toward a stranger truth, one that slips through our everyday sense of time like water through open hands. For light, time doesn't pass. It's a difficult idea to hold. You, after all, live in time. You move through it constantly, measuring, remembering, anticipating. Your entire life is woven from moments, from before and after, from not yet and too late. But light knows none of that. To understand why, let's revisit something Einstein gave us, a view of time not as an arrow, but as a dimension, like width or height, something that can stretch or shrink depending on how you move through the world. The faster you go, the slower time moves for you. At ordinary speeds, this effect is too small to notice. But as you approach the speed of light, the change becomes enormous. Time slows, seconds stretch, clocks drift apart, and at the speed of light itself, time stops altogether. Now, pause. Take a breath. Imagine what that means. A photon leaves the surface of the sun. You, standing on Earth. We'll say it takes just over 8 minutes to arrive. You might picture it soaring across space, dancing past planets, riding waves of radiation until it lands in your eye or warms your skin. But from the photon's perspective, if it can even be said to have one, there is no journey, no wait, no middle. It is emitted, and it is absorbed, instantly, seamlessly. No time has passed. There was no in-between. This strange, silent property of light opens a door into something deeper, that our experience of time is not universal. It depends on how we move. And for things that move at light speed, time is not a river, it's a frozen lake. This might feel abstract, but it ripples quietly through everything. Every star you see in the sky is sending photons across light years of vacuum. From your perspective, they're ancient. From theirs, they're newborn. And this paradox, the simultaneous truth of age and timelessness, is not a flaw. It's the universe's way of keeping everything stitched together. Think of time as a fabric. Most of us move slowly across it, feeling its texture, one thread at a time. But light doesn't move across the fabric. It is the thread, taut, instant, eternal. This helps explain why photons never decay, why they don't age, why a beam of light from the edge of the observable universe can still reach us, still deliver its message after billions of years. Because for that photon, no time has passed. It left, it arrived, just like that. Now, you might wonder, how can something exist if time doesn't pass for it? Doesn't existence require change, motion, sequence? But light teaches us another truth. That being doesn't always require becoming. That some things exist not through duration, but through presence. Photons don't remember their path. They don't look back. They don't look forward. They simply are. And that's enough. There's a gentle kind of awe in that, isn't there? That the most essential part of your sight, your warmth, your connection to the stars, is delivered by something that knows no time at all. That exists only as a bridge between things that do. You and the sun, you and a distant galaxy, you and the screen you're reading now. All of these things are linked by light, and in that linking, time disappears. In a way, photons are like punctuation in a story you're still writing. They arrive not to move time forward, but to mark where understanding happens, where one thing touches another. And yet, for all their timelessness, photons let you measure time. Think of how you define a second, not by a clock on a wall, but by light itself, specifically. The vibrations of light within cesium atoms, our most accurate clocks, atomic clocks, count time using light's steady, unwavering rhythm. Even though light experiences no time, it provides the rhythm by which we mark it. There's something beautifully circular about that. Time, defined by a thing that doesn't experience time. It reminds you that constancy can arise from paradox, that stillness can emerge from motion, that the fastest thing in the universe is also the one least touched by the passing of moments. Tonight, as you lie in your quiet space, perhaps you feel your own sense of time soften, not because you're moving faster, but because you're listening differently, because you're allowing yourself to float like a photon, through stillness. No rush, no waiting, just presence. You're still breathing. The room is still here. The world continues around you. But inside that awareness, there's a stillness, not of emptiness, but of completeness, the kind that photons carry effortlessly, every moment of their brief and boundless lives. In the next part of our journey, we'll look more closely at those waves, the colors, the stretches, the squeezes that make light not just a carrier of energy, but a language of emotion. We'll ask how all light moves at the same speed, and yet looks so different. How red can mean slow and far, and blue can mean close and hot. But for now, let this linger. Some things move so fast, they leave time behind, and in doing so, they bring us closer to understanding it. You linger now in that strange stillness, where light travels but does not age, where a journey can happen without the passage of time, and yet, within that timeless stream, there is variety, waves of difference, pulses of identity, because not all light is the same. It moves at one speed, yes, but it speaks in many voices, the voice of color. Open your eyes in the daylight, and you see a world painted in blues and greens, the warm reds of evening, the silver hush of moonlight, the pale gold of dawn. All of these are simply light, just photons, humming through space at the same pace, but each carrying a different song. That song, its tone, its pitch, its signature, is what we call wavelength, or frequency, if you like the rhythm of it better. Light, though always swift, comes in waves that stretch and squeeze through space, creating the palette of what we see. Red light waves are long and slow. They ripple like lazy waves across a quiet lake. Blue light waves are tight, fast, more energetic, like the shimmer of a struck string. Violet and ultraviolet move even more tightly, nearly brushing the edge of invisibility. And beyond those limits, there are waves we cannot see at all. Infrared, microwave, radio, X-ray, gamma. All of it is light. All of it moves at the same unshakable speed through empty space. And yet, the feeling each type of light gives, the energy it delivers, is entirely different. Imagine a single beam of white sunlight shining through a prism. On one side, it's pure and blended, undivided. But once it passes through that little wedge of glass, it separates red, orange, yellow, green, blue, indigo, violet. A rainbow spilled from a single beam. Not because the light slows or hurries, but because its waves bend differently as they pass through matter. It's like watching a crowd of dancers move across a floor that's just slightly uneven. The longer, slower waves turn gently. The tighter ones swing wide. They don't break the rule of speed, but they reveal their nature by how they bend. This bending, this gentle separation, is how we come to see light not just as motion, but as meaning. Different colors mean different temperatures, different moods, different distances. Look at a flame. The red flicker is cooler than the blue heart. Look at the sky. Its blue is the scattering of short waves by the air, while the red of sunset is what remains when the blue has gone wandering. Look at the stars. Red ones are older, cooler. Blue stars burn hotter, younger, more fierce. And even galaxies, those vast cities of starlight, reveal their movements by their color. When a galaxy moves away from us, its light stretches. The waves lengthen, shifting toward red. We call it redshift. Not because the galaxy is changing color, but because the space between us is growing, pulling the waves like taffy. And when a galaxy moves toward us, the opposite happens. The waves compress. The light becomes bluer. This blue shift isn't about speed alone. It's about motion across a fabric that itself is stretching, expanding, reshaping the story of light as it travels. Through this simple stretching of waves, we can measure the heartbeat of the cosmos. We can tell how fast galaxies are receding, how far ancient stars have drifted. We can even estimate the age of the universe by watching how the earliest light has softened, cooled, become a low hum that bathes everything, the cosmic microwave background, a ghost of the Big Bang, still whispering in the static between radio stations. And all of this, the stretching, the shifting, the dancing of light's many hues, still happens at the same constant speed. Because while wavelength changes and frequency changes, the speed of light itself remains unbothered. It's like watching runners on a track. Some take long, easy strides, others dart forward in quick bursts. But they all move at the same average pace. Their style is different. Their rhythm is unique, but their destination and the time to get there is shared. This sameness is what makes light such a reliable narrator. When we study the light from distant places, we're not just seeing images, we're reading timelines, histories. The difference in color tells us how long the light has traveled, how much the universe has stretched around it, how far its source has fled from where we now lie. It's easy to forget in our day-to-day lives. How extraordinary that is. The red of a sunset is not just pretty, it's a bending of ancient rules, performed right above the horizon. The glow of a neon sign isn't just color, it's electrons jumping and falling, releasing photons at specific frequencies. The hum of your microwave is light too, only with waves so long you can't see them, though they cook your soup all the same. Light is everywhere, and always on time, and within its constant speed, it carries infinite diversity. No two photons are identical in path or purpose, yet all obey the same pace, the same limit, like 1,000 instruments all tuned to the same tempo, each playing its part in the song of visibility. Tonight, as your body rests and your eyes grow heavy, you might imagine light not just as motion, but as music, a song that never ends, a rhythm that holds the universe in place, a melody written in red and blue, near and far, cool and warm, a single speed, endless expression. In the next part of our journey, we'll follow that music into the presence of something massive, something so heavy, so dense, that even light can't escape it. We'll explore how gravity bends not just space, but light itself. How even the fastest thing in the universe must bow to the weight of something larger. But for now, let this moment settle. Light moves only one way, always at the same pace. But within that pace lives every color you've ever seen. The colors still echo softly behind your eyes, each hue a rhythm, each ripple a tone carried perfectly by light, moving at its unfaltering speed. But now, you begin to sense that the universe isn't just a canvas of color. It's a stage with curves, a surface that warps and bends beneath unseen weight. And even light, for all its swiftness and purity, must follow where that stage leads. Because gravity does not pull like a rope, it bends like a whisper, and light, though massless, cannot help but listen. Imagine shining a flashlight through space, not in a straight hallway, but across a trampoline where a heavy ball rests in the center. If you aim your beam near the ball, the light curves inward, following the dip in the surface. It doesn't veer off track out of confusion or resistance. It simply takes the shortest available path. And when space is curved, the shortest path is not a straight line. That's what gravity does. It doesn't grab light. It reshapes the space light travels through. It doesn't need to pull photons in. It merely changes what straight means in their world. This idea, once shocking, is now quietly accepted. Thanks again to Einstein. When he published his general theory of relativity, he changed the story of gravity from a force to a feature. Space and time, he explained, are not passive backdrops. They stretch and flex in response to mass and energy, and in doing so, they guide everything that moves, including light. This bending has been observed, measured, even captured in photographs. During a solar eclipse in 1919, starlight that passed near the sun appeared displaced, slightly shifted, as though space itself had tilted. The stars hadn't moved, the light had curved, and in that subtle arc, Einstein's bold predictions were confirmed. You may not feel it now, but gravity is curving the path of light all around you, from the sun, from the moon, from your bedside lamp. On Earth, the effect is small, almost imperceptible, but in deep space, near massive objects like black holes or neutron stars, the bending becomes dramatic. Sometimes, light curves so sharply it circles around a galaxy and arrives at our telescopes from multiple directions at once. This is called gravitational lensing, and it allows us to see distant galaxies magnified, split, or mirrored, not because their light changed, but because the space it passed through was curved like glass. And sometimes, light cannot escape at all. Near a black hole, space-time bends so steeply, so abruptly, that even light loses its path. Once a photon crosses the event horizon, it cannot return, not because it has slowed or weakened, but because the space ahead is too steep, and the light has no direction left that leads outward. This is not a wall, not a trap in the conventional sense. It is simply the ultimate downward curve, the edge of possibility. Beyond it, all paths lead inward. The light may still be moving at the same constant speed, but the geometry has turned all roads back. This shows us something vital. Even the fastest thing in the universe isn't exempt from the structure around it. Light has no mass. Light cannot be held. And yet, light obeys the curves of gravity like threads sliding through cloth. There's something humbling in that, isn't there? That even light, this pure, massless traveler, must bow to the contours of space, not because it's weak, but because the shape of reality leaves it no other way. And still, it carries on, through warps and wells, around galaxies and into shadows. The constancy of its speed remains untouched. Only its path changes, its direction, its angle, the route it takes to reach you. Now, close your eyes and imagine standing near a black hole, not close enough to fall, but close enough to feel the change. You shine a light upward, away from the dark center, and as the beam rises, it redshifts. Its wavelength stretches, its color softens, not because it's losing energy, but because climbing out of the curved space requires effort. Eventually, the light grows so red, so stretched, that it fades beyond visibility, not stopped, just softened out of reach. This is what happens near extreme gravity. Time slows, light stretches, paths bend, but still, the speed of light remains untouched. That's what makes this all so delicate. The speed is constant, but the space it travels through is not. And when space bends, light follows. This is how we map the dark, how we see the unseen. Black holes don't glow, but the light that bends around them tells us they're there. Galaxies far behind other galaxies send us their light in multiple arcs and smears, distorted like a fingerprint pressed into a lens. And from those shapes, we infer mass, curvature, presence. Gravity is the artist. Light is the brush stroke. And we are the eyes that read it. Tonight, maybe you imagine the universe not as a grid, but as a quilt, soft, curved, tugged downward by mass and time. And through that quilt, photons move like stitches, pulled straight, but never truly straight. The stars you see are sending light along paths bent by everything that lies between. And yet that light still reaches you, not late, not lost, just curved. In the next part of our journey, we'll look at what happens when light slows down, not in space, but through materials. What does it mean when a beam of light enters glass or water and seems to hesitate? Why does it bend? How does it regain its speed? And is it really slowing down? Or is something else at play? But for now, let this image settle into your resting thoughts. Even light must yield to gravity, not in speed, but in direction, not in spirit, but in path. The curves of space still ripple behind your closed eyes, and the thought of light bending, not because it wants to, but because space itself is no longer straight, still lingers in your chest like a breath held gently. But now, we shift from the vast stretches of the cosmos back into the more familiar. A glass of water, a window pane, a prism on your desk catching sunlight. Because here on Earth, we've all seen something curious. Light slows down. At least, it seems to. When a beam of sunlight enters water or glass or even the lens of your glasses, it bends, it refracts, and it appears to travel more slowly. The same photon that raced through empty space at the universe's top speed now seems to hesitate, to linger, to take its time. But what does that really mean? Does light change its mind? Does it forget its speed limit? Not quite. Let's take a moment to walk with a single photon. Imagine it leaves the air and slips into a pane of glass. In the vacuum of space, or even in air, it moves unobstructed, a clean, unbroken path. But inside a material, the journey gets complicated. The photon doesn't just glide straight through the glass. Instead, it interacts, not violently, not destructively, but in a dance. It's absorbed and re-emitted by atoms within the material, again and again, a kind of polite, repeated interruption. The photon moves forward, is absorbed by an electron, which jumps to a higher energy state, then falls back and releases a new photon. That new photon continues on, only to meet another atom, and the dance repeats. Each of these little exchanges takes a moment, not much, not even enough to notice individually, but collectively, they add up. The photon seems to slow down, not because its speed has changed, but because the path has become stop and go, like trying to drive through town with every light turning red just as you arrive. The actual motion between atoms, between those interactions, is still at the speed of light. The delay is in the rhythm, in the interruptions, and the denser the material, the more frequently the photon interacts. That's why light travels more slowly through glass than through air, and more slowly through water than through vacuum. But it never truly stops. Even in the densest transparent materials, even when bent, scattered, delayed, light remains persistent. It will find a way through, step by patient step. And here's something magical. Once the photon exits the material, it instantly resumes its full speed. No recovery period, no rebuild, just immediate return to the cosmic tempo. Imagine that. You're sprinting. You're slowed by a crowd, forced to zigzag and pause, but the moment the space clears, you're back at full speed, as if the delay never happened. That's what light does, over and over again. And the bending, the refraction, that, too, is a story of rhythm and speed. When light enters a slower medium at an angle, its wave fronts adjust. The part of the wave that enters first slows down first, while the rest is still moving faster. This difference in speed shifts the direction, bending the path like a marching band turning a corner when one row steps into mud before the others. That's why a pencil looks bent in a glass of water, why the bottom of a pool seems closer than it is, why rainbows curve and shimmer. These are not tricks. They're the graceful consequences of a photon's relationship with the world it moves through. It honors the speed limit, even when the road changes texture. Even opaque materials, like walls, metals, your own skin, are not absolute barriers. They're just places where photons are absorbed rather than passed along. Their energy is still conserved, still transformed into warmth, motion, or chemical change. But the photon's visible journey ends there. It's a reminder. Light is tireless, but not invincible. It gives itself completely without holding anything back. You might wonder now, why do we say the speed of light is constant if it changes in materials? And the answer is that the universal speed limit, that 299,792,458 meters per second, is the speed of light in a vacuum. It is the speed at which information and causality travel through the universe when nothing gets in the way. In other media, light's effective speed drops. But this isn't a failure. It's a dance between the photon and the matter it traverses. A soft slowing, not of light's true nature, but of its apparent pace. And if you ever feel stuck, slowed by life's obstacles, perhaps remember the photon. It doesn't quit. It doesn't argue with the atoms. It passes through, step by step, interaction by interaction. And the moment it finds open space, it flies. Tonight, as you lie in stillness, the room around you is full of tiny delays. The light from a screen reaching your eyes has passed through glass and air and water. The colors in your room bend and shift based on the surfaces they strike. The photons in a single candle flame travel through hot, dancing air, flickering with every tiny change in density. And yet, you perceive it all as seamless, as one gentle flow. In the next part of our journey, we'll stretch our minds a bit more, imagining a universe where something could go faster than light. What would that mean? What rules would break? Would time still make sense? But for now, let this thought carry you. Light may slow, it may bend, it may stumble, but it never forgets how to move, and never forgets where it's going. The image of the photon still lingers, unbothered, unhurried, slipping through obstacles with the patience of something that always knows the way forward. But now, your mind stirs with something more mischievous, a gentle rebellion, a question whispered in the quiet folds of imagination. What if something could go faster than light? Not almost, not nearly, but truly faster. It's a strange thing to consider, because in all the physics we've discovered, light's speed is the hard edge, the cliff at the end of the possible. And yet, wondering about the impossible has always been how new ideas are born. So, let's wonder slowly. Let's imagine something. Call it a superluminal traveler, a particle, or a signal, or even a person in a fantastical ship, capable of leaping beyond light's barrier. What would that feel like? What would it break? To begin with, it would untangle time, not stretch it, or pause it, or warp it, but unravel it completely. Remember that light defines not just how fast things can move, but how cause and effect are ordered. If something could move faster than light, it could reach a place before the photon gets there, before the signal, before the cause. You could shout before you opened your mouth, answer a question before it was asked, arrive at a destination before you left. Not in a metaphorical, poetic way, but mathematically, precisely, alarmingly. From your perspective, you may have traveled from point A to point B in what felt like a natural progression. But for someone else, moving differently through space or simply observing from another angle, it might look as if you'd gone backward in time, that your arrival happened first, that your departure followed later. And here's where the trouble begins. Because if events can arrive in the wrong order, then paradox becomes more than fiction. You could interfere with your own past, prevent the very thing that allowed you to act in the first place. And if that happens, then what? The universe, as we understand it, is built not just on laws of energy and matter, but on consistency, on sequences that hold together, not because we wish it so, but because logic demands it. Faster than light travel would threaten that. It would unravel the cause-effect tapestry we rely on for everything from heartbeat rhythms to planetary motion. Even the flicker of thoughts in your brain depends on events flowing in the right order. And yet, there are places in the equations, tiny cracks in the marble, where hints of possibility still shimmer. Some physicists have imagined particles that always move faster than light. They've given them a name: tachyons. Purely hypothetical, never observed, but intriguing. Tachyons, if they exist, would be born beyond the speed of light and never slow down. But here's the twist. They couldn't be used to send information. You couldn't control them, aim them, or predict them in a useful way. They'd exist in a realm outside communication, like whispers behind a closed door, present but unreachable. Other minds have dreamed of warping space itself. If nothing can move faster than light through space, maybe we could make space itself move, compressing it in front of a ship, stretching it behind, like riding a wave, not cutting through the water, but letting the water carry you faster than any stroke ever could. This is the idea behind warp drives. Still theoretical, still speculative, but gentle in their elegance, because they don't break the speed of light. They move the road. Even wormholes, those shortcuts through space-time popular in science fiction, obey the rule. They don't allow travel faster than light in the traditional sense. They simply fold the map. A path that looks long becomes short. A journey that would take years becomes a step. Not because the traveler speeds up, but because the distance shrinks. In every one of these ideas, the universe seems to whisper a warning. You may not break the rule, but you may walk carefully around it. And perhaps that's enough. Perhaps the boundary matters not, because it's meant to frustrate us, but because it protects something essential. It protects the flow of time, the clarity of memory, the stability of everything we call real. Still, your imagination may linger. You may wonder, would it feel any different to move faster than light, to leave photons behind? And the truth is, we don't know, because nothing with mass has ever done it. Nothing with structure or memory or mind. We are creatures woven into time, our atoms bound by inertia, our thoughts shaped by sequence. To step outside that rhythm would be to become something else entirely, not faster, but unanchored. And if there is a beauty in that idea, there is also a kind of loneliness, because even the stars you wish upon obey the limit. Even the galaxies spinning at the edge of visibility cannot outrun it. The speed of light is a tether that binds us all, however loosely, in a shared tempo. Tonight, as you rest, perhaps you can feel the comfort in that nothing moves too quickly to be understood, that no message arrives too soon to be heard, that even the vastness of space unfolds with a patience that matches your breath. In the next part of our journey, we'll return to this idea of limits as gifts. We'll explore how the speed of light doesn't just restrict, but gives shape to reality itself, how boundaries can define beauty, and how, by not going faster, we see more clearly. But for now, let this question drift like a bubble into your thoughts. What if you could go faster than light? And what if, in doing so, you lost the very meaning of motion? The question still hums quietly in the back of your mind. What if we could go faster than light? You feel its glow like the fading trace of a dream, enticing, daring, but also unsettling. Because to move beyond the speed of light isn't just to travel faster. It's to step outside of sequence, to untether from time, to risk losing the very shape of things. And so now, we soften the question. Let go of the what if, and instead return to what is, to the quiet brilliance of a universe built with boundaries. Because sometimes, the most beautiful things arise not from freedom, but from limits, from structure, from rhythm. Light's speed limit isn't just a cap, it's a framework, a shape, a silent agreement between space, time, and energy that allows the universe to remain coherent, unfolding gently, moment by moment, like a book with its pages in perfect order. Without the limit, stories fall apart. And you are, in the end, a story, a living narrative of thoughts, memories, and sensations that depend entirely on the proper flow of time. Imagine, for a moment, trying to read a novel where every chapter arrived all at once. You wouldn't be able to follow the plot. You wouldn't even know where it began. The beauty would vanish in the noise. That's what the speed of light prevents, chaos through simultaneity. It ensures there is a before and after. It gives your memories somewhere to live. And it gives distance meaning. If light could arrive instantly, the concept of space would dissolve. Far and near would blur. You wouldn't know whether a star was distant or simply dim. The age of a galaxy wouldn't matter, because you'd see its present, not its past. But instead, light carries the story of what was. It brings the past into the present with just enough delay to make time visible. You see stars not as they are now, but as they once were. You see sunlight not in the moment of its creation, but 8 minutes later, softened by travel. This delay is not a flaw. It's a gift. It lets you look into the deep past without ever leaving your home. Every night sky becomes a time machine. Every beam of starlight a quiet historian. And so, the boundary becomes beautiful, not because it restrains, but because it reveals. Like the edge of a painting, the frame of a song, the limits of a page, the speed of light shapes the canvas on which all events are painted. It allows for patience. Without it, there would be no waiting, no wonder, no soft unfolding of discovery. Everything would arrive at once. And in that rush, nothing could be appreciated. But with the limit, there is always just enough time. Time to notice, time to question, time to marvel. There's also balance. The speed of light sets the scale for all physical interactions. It keeps energy and mass in proportion. It defines the relationship between electricity and magnetism. It shows up again and again in equations, not as an add-on, but as a foundational thread. Without it, those relationships would collapse. Reality, as we know it, would deform. Gravity wouldn't curve space correctly. Atoms wouldn't bind. Even colors might not exist in any recognizable form. The more you look, the more you see. The universe is not just tolerant of this limit. It's dependent on it, structured by it, harmonized around it, like a symphony that plays not louder and louder, but in tune. This is the quiet brilliance of boundaries. And in your own life, you've felt this too. You've known the calm of a routine, the grace that comes from structure, the small freedoms that grow only when held in a shape. You've seen how time itself gives meaning to experience. A flower blooms not all at once, but slowly. A song moves from note to note, and it's that separation, the space between, that makes it music, not noise. Even breath depends on pause. Inhale, hold, exhale. Light follows the same rhythm, not in how it moves without rest, but in how it arrives. It reaches you in waves, in photons, in subtle delays that give the world its texture. Tonight, the light touching your eyelids has traveled far, some from nearby lamps, some from distant stars. All obeyed the same rule, all moved at the same pace. None arrived early, and none needed to. That's the wonder, that the fastest thing in the universe is also the most patient. It does not rush, it does not demand attention, it simply moves forward, quietly and constantly, within the boundary that defines all possible motion. In the next part of our journey, we'll follow light's constant speed into the heart of quantum mystery, into the realm where particles can seem to dance with each other across vast distances without sending signals, where the rules of speed and distance bend into something stranger, something softer. But for now, settle into this truth. Not everything needs to be faster. Not every story needs to leap. Some truths are meant to unfold, and the speed of light, unchanging, unwavering, makes that unfolding possible. It isn't just a limit, it's a lullaby, a constant note humming in the background of everything. And tonight, it sings you towards sleep. That lullaby of light still hums in your mind, steady, gentle, impossibly fast. It brings order, rhythm, and time itself into focus. But now, as the universe dims a little more around you, a new question stirs just beneath your breath. If nothing can go faster than light, then how do entangled particles seem to break the rule? Welcome to the edge of understanding, a place where light, limits, and logic begin to blur into something stranger, something softer. Because deep in the heart of quantum physics, there exists a phenomenon that feels like a whisper passed between stars, a thread stretched across space, where two particles, once connected, remain connected, no matter how far apart they drift. This is called quantum entanglement, and at first glance, it seems to violate everything we've built so far. Let's imagine this gently. Suppose two particles are created together in a way that links them, like twins born in the same moment. You separate them. One stays with you. The other journeys far, far away. Light years, perhaps. Now, if you measure the state of your particle, say, its spin, you instantly know the state of the other. No delay, no signal, no photon traveling between them. Just immediate knowledge. Einstein didn't like this. He famously called it spooky action at a distance. It seemed to clash with everything his relativity had taught us, that no information could travel faster than light, that causality had to be preserved, that all things, even particles, should obey the cosmic speed limit. And yet, experiment after experiment has confirmed that entanglement is real. But what does it mean? Does it break the speed of light? Does it allow messages to be sent instantaneously across the universe? Not quite. And here is where the magic stays intact. Entanglement does not allow for communication in the traditional sense. You can't use it to send a message faster than light. You can't control what the outcome of a measurement will be. You can only observe it, and once you do, the entangled partner responds in kind. But until then, until one particle is measured, neither particle has a definite state. They exist in a cloud of possibilities, a kind of shared uncertainty. What travels between them is not a signal. It's something gentler, something more like a memory, a pattern, a coordination that exists outside of space as we know it. It's not that the particles are talking to each other faster than light. It's that they were never truly separate to begin with. Even as they move apart, their properties remain part of one whole, like notes in a chord, sounding together no matter how distant their instruments. So, the speed of light is not broken, the boundary remains, but our understanding of connection grows deeper, stranger, more subtle. It suggests that the universe, at its smallest scales, is not built only of individual pieces. It is also built of relationships, of interwoven possibilities. And those possibilities can stretch across space without being bound by distance. Light still sets the tempo, but entanglement shows us that not everything dances alone. You might picture the universe now not as a vast expanse of scattered dots, but as a shimmering web, a tapestry woven from threads of interaction, some visible, like photons moving between stars, and some invisible, like entanglements that span across galaxies without ever moving at all. It's easy to mistake this for communication, to imagine faster-than-light messages flying across the stars. But that's not what entanglement does. It's more like two perfectly synchronized dancers, separated by a curtain, each one moving in step, not because they see each other, but because the choreography was written before the curtain ever fell. This is why quantum mechanics doesn't violate relativity. It expands it, softens its edges, invites us to think not just about speed and distance, but about connection itself. And perhaps that's the deeper message of light's speed limit, not just that there is a maximum pace, but that pace isn't everything. There are other ways of being in sync, other ways of touching without moving, other kinds of closeness. Tonight, as you rest, maybe you feel that even across vast distances, there can be connection, that even when words are slow and messages delayed, something deeper can remain immediate, a memory, a presence, a bond, like the way you still feel a loved one's voice even when the room is silent, or the way a childhood song finds you in your dreams, years after the last time you heard it. These are echoes of entanglement, not in physics perhaps, but in feeling, and they live within the same rules, the same tempo, the same light, because even as photons rush along the edges of space and time, setting the speed of everything that can be known, entanglement hums beneath, not breaking the rule, but reminding us that not all meaning travels. Some of it simply is. In the next part of our journey, we'll return to the human scale, to the light that touches our lives every day. We'll explore how, despite its abstract speed and cosmic nature, light remains intimate, how it reveals our world, feeds our cells, and wraps our memories in color. But for now, rest inside this paradox. Light moves fast. Entanglement doesn't move at all. And both are real, both are necessary, and neither breaks the silence. The idea of particles entangled across galaxies still shimmers faintly in your thoughts. Strange, gentle, impossible to hold. And yet, now, we drift back from the edge of abstraction, back from spooky action and timeless photons, from bent space and silent limits. We come home again, to light as you know it, light as you live it, because even though it defines the rhythm of the cosmos, the speed of light is not some distant concept. It's in the room with you now. It brushes your skin, it softens your shadows, it brings you warmth, color, memory, and time. It is not only a constant in physics, it is a constant in you. You wake by it, you eat by it, you fall asleep by it. Your days are carved by the sun's arc, and your nights shaped by what light leaves behind. This rhythm of light and dark doesn't just mark your schedule, it sets your biology. Your circadian rhythm, the internal clock that tells your body when to sleep and when to rise, is deeply tied to the presence, absence, and timing of light, not just brightness, but hue. Morning light is blue-tinted, cool, and alerting. Evening light shifts redder, gentler, coaxing the body towards stillness. Even without clocks, your brain would still know what time it is, because light tells it so. And it does more than that. Inside your eyes, special photoreceptors send information not just to your visual cortex, but to your hypothalamus, where hormones are managed. Light triggers melatonin suppression in the morning and encourages its release at night. It literally changes you each time it touches your skin. But not all light is sunlight. Think of the glow of a phone, the hum of a computer screen. These are artificial suns, often shining at the wrong time. They speak the same language, photons traveling at light speed, but the message can confuse your body. Midnight feels like noon, and suddenly, sleep becomes a puzzle. This is the modern dance with light. We are surrounded by it, bathed in it, but sometimes overwhelmed. We forget that light has both power and precision. It was never meant to be constant. It was meant to arrive, still, It guides us. Think of how you navigate your world, not by shapes alone, but by what light reveals. A face in shadow becomes a stranger. A room without sunlight feels smaller. A familiar space, lit by candlelight, transforms into something quiet and warm. Even memories are colored by light. A childhood morning bathed in golden slants through curtains. A winter afternoon dimmed into soft gray. A beach at sunset, the sky folding into violet. Your mind doesn't just remember events, it remembers the light they arrived in. Photons carry emotion, not because they feel, but because they are the paint in which feeling is stored. They give shape to the invisible. They make memory tangible. And though we often think of light in visual terms, it touches every part of us. Plants live by it. Through photosynthesis, they capture photons and turn them into sugar, into growth, into life. And through plants, we live too. Every meal, every breath, every moment of warmth in your body is, at its deepest root, fossilized sunlight. Energy borrowed from photons long ago captured in green leaves. You are, in a quiet way, made of light. And not just physically, culturally too. We speak in metaphors of it. We talk about seeing the light, being enlightened, shining a light on the truth. Darkness becomes a symbol of confusion, fear, the unknown. And light is always what brings clarity, direction, hope. This is no coincidence, because to live is to see. And to see is to welcome photons into your body. You don't passively observe light. You absorb it. You let it in, and it never arrives late. From the smallest flick of a match to the ancient starlight that reaches your eyes from billions of light years away, all light obeys the same quiet promise. I will move as fast as I am allowed. No faster, no slower. This constancy gives light its strange intimacy. It always shows up exactly when it can. It doesn't skip ahead. It doesn't lag behind. It is, in its very nature, on time, and in being on time, it becomes trustworthy. That trust lets us build with it. Lenses, microscopes, cameras, lasers, fiber optic cables that carry your voice, your stories, your memories across oceans at the speed of light. You are connected to others, not just by thought or feeling or care, but by photons dancing in glass. Light isn't just how you see the world, it's how you reach it. And still, for all its power, it remains quiet, gentle. It illuminates without judgment. It reveals without asking anything in return. So tonight, as your body slows, as the lights dim and shadows stretch long across your ceiling, you might realize you've spent your whole day wrapped in light, from the moment you woke to now, not always noticing it, but always shaped by it. And though it may feel like light is gone at night, it's only hidden, tilted beneath the horizon, softened into starlight, turned into memory. In the next and final part of our journey, we'll close the loop, gently returning to where we began. We'll let the speed of light guide us towards stillness, toward a soft kind of understanding. Not an answer, exactly, but a peace with the question. For now, just breathe in the presence of it. Light is fast, but never in a hurry. It moves not to escape, but to arrive. And somehow, in touching everything, it teaches us to slow down. And so, at last, you drift toward the quiet end of our journey. The path we've walked has wound through theories and starlight, lantern games and particles that whisper across space. We've sat with Einstein beneath imagined skies, traced photons through glass and gravity, watched light ripple in water and freeze in time. And now it's time to let it all settle, not into answers, but into stillness. Because this wasn't just a story about science, it was a story about rhythm, about the gentle constancy of something that moves faster than anything else, and yet never seems to rush. It was about the limit at the edge of all motion, the boundary that says, here and no farther, a cosmic speed limit. But what a beautiful limit it is. You've seen how it shapes the unfolding of time, how it preserves cause and effect, how it lets stories have beginnings, middles, and ends. You've seen how light speed allows memories to soften, how it carries the past toward you in waves of soft illumination, how it wraps even the farthest galaxy in the grace of arrival. And now, you feel it. That light does not need to be infinite to be wondrous. That by moving just fast enough, no faster, it becomes something we can live beside, something we can dance with. Because a light that arrived instantly would give you no time to notice, no time to pause, no time to wonder. It is in the waiting that we find reflection, in the slowness that we find space for awe. Even 186,000 miles per second, so fast it circles the Earth 7 times in a blink, is still finite, still measurable, still paced. And that pacing is a gift. It allows starlight to stretch. It allows stories to ripple through space. It allows your own thoughts to meander through memory as light plays across a photograph. It's why you can look into the night sky and see things that no longer exist. Things long gone, their final flickers still en route to your eyes. The universe becomes not just a place, but a moment unfolding, and you moving within it. You've learned that light isn't just something to see. It's something to feel, to follow, to rest in. It wakes your body. It tells your cells when to sleep. It wraps your world in meaning. It reflects from the eyes of those you love. It glows in candles and pulses through fiber optic veins beneath the ocean. It defines distance. It guards order. It gives every shadow its shape. And all of this because it has a limit, a ceiling, a rule, a line that cannot be crossed, and so becomes the frame around which everything else is drawn. It might seem strange, even frustrating at times, this idea that no matter how powerful, nothing can ever move faster. But tonight, maybe it feels different. Maybe it feels like comfort. Like knowing that, across all the chaos and complexity, one thing holds steady, one thing obeys, always. One thing does not argue or falter or bend. The speed of light, it will not waver, it will not rush, it will not break. And so, you can rest. Because in a world that often feels too fast, too overwhelming, too scattered, light remains perfectly on time. It will arrive when it's meant to. It always does. So you lie back now, maybe eyes half closed, your breath soft and slow. The walls around you fade into shadow. The sky beyond your window cools to blue, then gray, then something almost black, but not quite, because even in darkness, there is light. It hides in the stars. It hums behind your eyelids. It waits on the horizon. The sun will rise again tomorrow, not because it is hurried, but because it is ready, because light has already begun its journey. It is traveling to meet you even now, at the one pace it always keeps. It doesn't need to be faster. It only needs to be faithful. And so, wherever you are tonight, whether you're still half awake or already slipping into dreams, I hope this quiet journey has brought a kind of ease, not just knowledge, but rest. Because that is what light gives you too. It shows you the world, yes, but it also lets you close your eyes and know that when you open them again, something beautiful will be waiting. A soft sunbeam, a shadow on the floor, the face of someone you love, touched by morning. The light will be there. It always is. And so now, with the hush of photons still curling around you like lullabies, let the last thoughts of this story fall away. Let the rhythms slow. Let your mind drift, unhurried, into sleep, because you are traveling too, not across space, but through time. at the only speed that matters, the speed of being here, of noticing, of resting. Let the universe continue unfolding. You've seen enough tonight. Sweet dreams.